Next speaker is Dr. Rachid NOUICER from Brookhaven National Laboratory, and he will speak about experimental highlights on QCD medium properties at RHIC. Please.
Yes. Hello? Okay, good. Thanks. Here? Okay. I was thinking that right-handed should be to this side and left-handed on this side. It seems. As the share wish. Okay. First, I would like to thank the organizer for the invitation and as well for organizing this conference in this very nice and beautiful place, Quarkonia, which is very relaxing. And I'm going to talk about experimental okay. My talk will be focused on the experimental highlights and QCD medium property at RHIC. As you know, the RHIC sometimes with the relativistic heavy ion collider, we call it QCD machine. And because we really studied the latest QCD, the QCD matter properties, and as you see here is the QCD calculation, the density profile of this, the latest, and here with the machine, we try to study this property of this QCD matter. However, I would like to mention also that we have another machine which is at higher energy, which is the RHIC. This means we have two QCD machines, and both of them trying to study the QCD matter properties as well, the characteristic and the discovery. Last week we had a RHIC user meeting at Brookhaven National Lab where we had the 10 years anniversary of the perfect liquid, which is here I refer to quark-gluon plasma in heavy ion collision, which has been announced in 2005, and we are in 2015. This means mostly is 10 years. In the last conference of nucleus in 2012, my colleague Carl have been mentioned that we are doing the RHIC energy, the beam energy scan, but there was no result, and I will try to keep his promise that this conference, I will show the results from this beam energy scan, which mostly we're trying to map the QCD phase diagram. And we are looking to determine the energy at which the QGP signal, which has been seen at 200 JeV, turn off as function of energy. And we are hoping also to search for the critical endpoints from the phase diagram. Something which was not in our to-do list, but it was a big surprise, has been observed at RHIC and a small system like PLAD, and it was very exciting, and now it's became a very exciting topic at relativistic heavy at RHIC, as well as RHIC. And now we observe for the first time that there is collectivity in a small system like proton, deuteron, helium on the gold, where these flow components are not equal to 0. This is very surprising and very exciting topic right now. However, the last topic that I will talk, it's clear it will be Quarkonia, which is mostly as probe for hot and cold nuclear matter. And this is, we're trying to study the properties of this matter. And we'll talk about the Gibbs psi, epsilon as function of centrality, system size, as well as function of energy. However, as usual at this conference, we always show you what's the upgrade for the next conference, which will be in 2017. As I mentioned as an introduction, we had this anniversary of the perfect liquid discovery at RHIC. In 2005, the 4 experiments at RHIC, which is Phobos, Star, PHENIX, and Brahms, have been discovered a new state of matter which is strongly interacting, and it was called quark-gluon plasma, and the characteristics has a characteristic of a perfect fluid. And here the paper has been published, and this is the front page of Physical Review letter. This discovery has been released over the world in United States, as well in Europe, at Saint Courier, as well in the Science Daily. What's these discoveries? Before I go to the discoveries, I would like to mention that the RHIC, since 2000 have been provided a lot of collisions at this site of the experiments, And since 2000 up to now, 2015, each year provide mini collisions non-stop every year at different energies with different system size. And this is, I will try to summarize here. This is 4 experiments. There is Phobos and Brahms has been stopped in 2005. They ran from 1999 to 2005. And now we are left only with 2 big experiments. We have STAR and PHENIX. This is, which has been provided by the Relativistic heavy-ion collider since 2000 up to today, which is still we are taking the data of proton aluminum. As you see, we have gold. We have also deuteron followed by PP, which is the baseline for gold as a reference. After that, we're trying to study the cold nuclear matter in the D-gold. And after that, we move to copper. From that, we move to something more heavier, like uranium, as which you have a higher energy density. And after this new phenomena of collectivity in small system like a PLED, as have been seen at LHC, we start now to work in smaller system like helium gold, proton aluminum, and proton gold as well. This is for the system. But I would like also to point out that these collisions for gold has been mapped out over long range of energy from 7.7 in center of mass energy up to 200 GeV for gold. This means we have 70 as function of energy, and this is what we call beam energy scan at RHIC. This means we have extensive data at different energies, and what we have in 2005 is this is the big discovery. What RHIC discovered in 2005? The first thing, we have PP collision, which we formed the QCD vacuum, and here you have gold at 200 GeV when this new medium has been formed. And what we do, this is what's called the nuclear modification factor, which is just a ratio of the particles produced in this medium divided by the ratio of the divided by the particles produced in PP collisions, normalized by the number of binary collisions between these nuclei. If you do that, this is the plot, nuclear modification factor defined here as function of transverse momentum. Transverse momentum is the momentum of the particles from these collisions. What we observed, that there is a huge suppression by a factor 5 compared to 1 binary collisions of the particles. And this is what we call the jet quenching, which has been predicted a long time ago by the theories, Julassi and other groups. And this is really the experimental evidence that when the particles with high momentum go through the medium, they will be stopped and suppressed, and there is nothing come out. On the contrary, for the PP, if you have jet particles, and this is a vacuum, QCD vacuum, they go through it and they are not suppressed. This is strong indication that this medium has been formed in gold-gold collision at 200 GeV. However, also, we had to point out that at LHC, which is higher energy, with all the experiments, CMS and ALICE, and also ATLAS, has been shown this beautiful data. This is our most important plot, where we put the RHIC data, which is the pi0 and charged hadrons, on the top of the LHC data, and we see very nicely they agree with each other. These two facilities, RHIC and LHC, very nicely agree with each other, and the LHC can go to very high transverse momentum. This, the jet quenching discovery, is really confirmed by 4 experiments, as well by 2 facilities, RHIC and LHC. And if you look to SPS, this is the data that has been published. We don't see this suppression, but this suppression is characteristic of the RHIC and LHC. This is the major discovery. The next step now is what we call it the perfect liquid. If you take the particles produced from the collisions, and you look at the particles azimuthal angle distribution, which is mostly the Fourier expansion. And you can write this is the particle distribution. It has components we call the V2, V3, V4, V5. And this is component V2 is mostly when the 2 nucleus cross each other, they have elliptic shape, which is correspond to V2. You have the triangular shape, which is mostly the V3, etc., quadruple shape, the V4. This is just the distribution of the particles in this plane. You take the particles that you see for every component, and you plot it as function of the transverse momentum, which is the transverse momentum of each particles. and you plot this one here. This is the V3 for elliptic shape. This is the V2, the V3, and V4, and V5. And so also at LHC, they can go even to V6. This is the lead at higher energy. This is the gold at 200 GeV. Now, what we observe that the medium is strongly interacting. Why? Because we have V2 has very, very high. And if you take this data and you compare to the hydrodynamic viscous, which has IP plasma as initial state, and you compare to RHIC and LHC, and you put in the medium small shear viscosity to entropy density, which is this value, you found that you can reproduce the data only if these values are very small. And these values are very small, which is correspond to the liquid. And this is why we call it a perfect liquid, because there is nothing in the world has this viscosity, shear viscosity. This is what you call the liquid. And also, this we call fluid, and also at this moment, the property of this fluid remains to be determined. This is what we are doing right now at RHIC and LHC. We're trying to understand the property of this matter. This means the matter has been discovered, and now we are in the phase trying to understand the properties of this matter. And this is the main goal for the two facilities. Carl, in 2012, he mentioned that we are going to do the beam energy scan, and he promised you that in this conference we'll show you the results, and I will try to keep his promise by showing the result that the beam energy scan at RHIC. What we did, we take gold-gold collisions, and we map at every time the energy from 70.7 GeV in the center of mass up to 200 GeV here. And also we have LHC available data. And in the run 14, we add these two energies in the center of mass. This means we have plenty of data that we can see where the signature of this new state of matter can be turned off. How we do that is but vary the energy of all the range of the RHIC. Before I show you the results, I would like to mention to you how we are going to really proceed to look for the turn off of the QGP and on which energy. First, do we observe of turn off a new phenomena that have been observed in full energy scan? This means we have some results at 200 GeV, we change the energy, and we see if this signature goes away. If the signature goes away, we say, oh, okay, this is the energy where we have to focus between the hadronic matter and the transition to quark-gluon plasma. There is one measurement that we call constant quark number scaling. You take this Vn, which is, I showed you before, flow components, and you scale them by the number of quarks, and we see how this one persists or disappear at given energy. Sure, the most important is the jet quenching, at which energy the jet quenching goes away. A second topic which is interesting for the beam energy scan, do we see the critical endpoint from the phase diagram of QCD? And this is mostly that we are working on it by looking to the elliptic flow and also by looking to HPT measurement. This is the roadmap for the beam energy scan. Let's start step by step. This is the measurements of gold at 200 GeV. What we do, we take the flow components which are shown in the previous slide, which we have V2, V3, V4, V5, and we scale them by the constant quarks, and quark is equal to 2 if you take mesons, and equal to 3 if it's baryons. This means if you are talking about proton-proton, you divide by 3 to this component. If you take mesons, you divide by 2. This is for the, this is the V2, we have V3, and also we have V4, but the V4 has been determined with two methods, using 4-particle correlation or 2-particle correlation. What we see here, if you do the scaling and you plot this one as function of kinetic energy, which is defined here, is the transverse mass minus mass and the rest frame, which is this component here is transverse momentum. What you see that all the mesons and the baryons scale very nicely with each other, okay? This means I'm going to take this plot and see it at each energy. If the scaling fails, I will say something going on at this given energy. If the scaling persists, you will see how what's the conclusion. Let's take this one as a reference, And also I mentioned, because I mentioned PHENIX before, I have also to mention STAR, beautiful data. Here they show also the same data, V2 as function of transverse momentum, and this is for different centrality. This is minimum bias, all data, 0 to 80%. This is central collisions. This is mostly peripheral collisions. And here you see different particles, the phi and the protons and all the mesons and the baryons together, okay? If you take this V2 and you scale it as we did in PHENIX before, you find also very nice trend scaling. What we observe also that if you go to the peripheral collisions, the phi doesn't go with the scaling here. And because the phi, mostly if the matter is formed is hadronic, the phi, they don't interact. But if the medium is partonic, the phi will interact and they will scale. This means, based on this data, we suggest that the medium has been formed is partonic. To prove this is correct, we have to take a look to see the data as function of energy. Now we have a baseline. Let's now look to the data as function of energy. This is the same component that I showed before as function of kinetic energy. And here we look from 7.7 GeV up to 62 GeV.4, and I showed before 200 GeV. This means it's like the same. What do we see? As function of energy, first we see that elliptic flow up to from 20 GeV, 19.6 GeV, is mostly doesn't change. It's exactly the same. And we observe as well that the scaling is working properly for all particles. This means I cannot use this observable as an indication if the medium is partonic or hadronic. This means I should drop off. This observable, I should not use it as such. But what we, but what we see something interesting, that the phi mesons, they don't scale with other particles when you are below 19.6 GeV. Maybe something is going on with this medium, that the phi, if between here there is maybe some transition, maybe here there is a hadronic medium, but here is maybe is partonic. There is maybe something around 20 GeV going on between this and this. We can use the phi as a measurement. This means there is a hint here. At RHIC, we have two phases. We have beam energy scan phase 1, and we have beam energy scan phase 2. Phase 1 is done. Phase 2 is in 2019. The goal from the phase 1 is to narrow, to look for the short window or narrow the window where we have to find the phase transition between hadronic to quark-gluon plasma. But it seems maybe here from these measurements, it seems maybe around 20 GeV. But however, let's take a look about more data. One of the powerful measurements for the discovery of quark-gluon plasma, as I mentioned, is the jet quenching, which I showed this before. As a function of energy, we cannot do the nuclear modification factor because at each energy you have to do the same PP. We cannot do PP in each energy. It will take us forever. What we do here, we take gold at different energy, and we take the collision, the central data, central collision, and we divide it by the peripheral. Dividing by the peripheral, this means you are mostly dividing by the PP collisions, peripheral collisions. It's mostly RAA, but different definition. However, at 200 GeV, we see there is a expression. As function of energy, this expression disappears. However, always when you go to the low energy, you don't have enough statistic because the luminosity of the beam decreases dramatically. What we have here, it seems, if you want to look for the energy, the phase transition or between partonic to hadronic, maybe there is something going on in this region between, let's say, 40 GeV and 20 GeV, but we need more statistics to go here. This means in the next phase of the beam energy scan, we have to focus, I can say, between 20 to 40. This means the window now is getting narrower and narrower. You don't need to go to 62 GeV. You know it's already expressed. However, because we don't have data at very high PT, we can look to the calculations. There is some calculation available. They say here, this is the for RCP, 10 GeV, 20 GeV, and 40 GeV using QCD plus cold nuclear matter for different particles. If you look very carefully here, at 40 GeV, they are saying is expressed but at 20 GeV, they say it's not spread, and they can go to high PT. This means we have to focus around between 20 GeV up to this region here, less than 40 GeV. This means the window of the surge or the phase transition is narrow. Okay, let me go a little more faster. The second observable is interferometry, which is HBT measurements. We can imagine that this is the two nucleus crossing each other, and when they cross, if you know the Bjorken crossing each other, they form a cylinder between them. And this is the side view of the cylinder, and here HBT say this is R long, is mostly the expansion of the collision toward the Z direction. If you look to the front of the cylinder, you have in the y-axis we call R out, and this x-axis we call R side. This is mostly give you the dynamic of the collision. If I take this, which we define here, and make R out minus R side, this is mostly sensitive to the duration of the collision. Let's plot this one here, quantities, as function of energy. If I plot this quantity of the dynamic as function of energy, I see something going up and after it goes down. We put also RHIC data here. And this is a star and star PHENIX data, and high energy is Alice. If you plot this one, they tell you there is a peak around between 20 to 30. That's mostly maybe there is something going on here. This means the phase two program is going to focus between 20 to 40 GeV, and you look if maybe we can find critical endpoints. This is mostly the outputs, and the work is in progress about this search for Quarkon plasma and transfer. Something very interesting that I have to show, very important, is the discovery about this collectivity in small system. CMS in 2012, 2003, 13, they show this beautiful data, elliptic flow as function for different centralities, and they show there is a collectivity in lead as well. There is a PLED, and the amplitude between the two are exactly the same, which is very interesting. They show also there is a V3 is not really equal to 0. We are expecting there is no collectivity in the PLED, but there is something. Very quickly, when they saw this result, they asked us, do you see something in 200 GeV? Ajay is trying to say that RHIC and the RHIC, they are not independent. They work with each other, and they try to understand this observable as function of energy. This means sharing the data between us is one of the most important tasks that we have. If you look for the D gold at RHIC at 200 GeV and 5.02 at RHIC for the PLED, you see that there is also elliptic flow in D gold, and is similar to the RHIC, and is mostly independent of energy. If we put the data on the top of each other, RHIC versus the RHIC, for two centrality, they agree 100% with each other. That collectivity exists in this small system, and we are thinking in the beginning it's only in the large system like gold or lead, but this is something new. After that, as I showed before, we don't see the V3 for the D gold. This is the energy density profile from the global calculation for PLED, D gold, helium gold. As you see the energy density profile, that helium gold is completely different, and we think maybe there is some fluctuations there. If you do the measurements, we see that the D gold doesn't have the V3, but the helium gold has a V3. It's maybe this V3 is related to fluctuations, and V2 between D gold and helium gold are exactly the same, beautifully. As the message from the part that I just showed, there is a new result at RHIC and the RHIC for the small system, and this new result of the small system open a lot of questions, and we don't have the answers yet. Now, the last part of my talk is the Quarkonia. The Quarkonia, we use it as a probe for the hot and cold nuclear matter. This means why we study Quarkonia is to learn about the thermal property of the QGP. This means if you have one, for example, gypside, heavy quarks, go through the medium at T0, and this is T less than critical temperature. It will nothing happen to it. It will come in and go out, and the yield of this particle is exactly the same. But if you go to some medium where the temperature is very high, higher than critical temperature, this particle will melt, and it will combine with other quarks, light quarks, and they will be completely suppressed. This is one way, very quickly I show how we can do a study of the hot and cold nuclear matter. We change energy, we change centrality, as well we look for the momentum, rapidity, and we look for the breakup and cold versus hot cold nuclear matter. First, let's show you the result of the GPSI go to forward rapidity region, which is as function of centrality. We know that when you go more central, you have more hotter medium. This means they are more suppressed. And this is at forward rapidity region. The most important here, which is very interesting, is if you do this for different energies, 39, 62, and 200 JeV, you don't see difference. And we don't understand yet why this is independent of energy. Now, if you look forward rapidity versus mid-rapidity region, the behavior also is suppressed and exactly relatively the same. Another interesting result is now we are going to change the system size, copper, gold, and uranium, and you look this one as function of centrality. We found it also is independent of the system size. Again, we don't understand it, why it's happening. From the experimental point of view, we have a lot of data, we'll have a lot of open questions, but at this moment, the theorists are running behind. We don't see any paper coming out tell us what's going on here. But the measurements is going on at RHIC as well. And also here, if you look for copper, gold, you see that this melting of this heavy quarks, Quarkonia, is getting more and more when you go to central region. This result was not expected before we did these collisions. And right now is very interesting and intriguing to the field as well in the both facilities, RHIC and RHIC. Here I am trying to summarize the result of the Quarkonia. This is RHIC, this is RHIC, beautiful data of RAA as function of the binding energy, which is the energy keeping these two heavy quarks together inside this particle. This is epsilon state, 1s, 2s, 3s, you have a GPSI, and this is at RHIC. Results at AA support the idea of Quarkonia dissociation, which has, when these heavy quarks go through the medium, and the medium is hot, this will be dissociated and will melt the medium. This means the idea of device screening, it seems, is working. This needs to be understood also in our theoretical point of view. Going to my conclusion. Upgrade for the future, 2017. This is an upgrade for SPHENIX. PHENIX is going to move SPHENIX, super PHENIX. And there is a new upgrade, and mostly the physics is to study the jets and increase the kinematic. And also, to enhance, resolve the epsilon mass state. This means we have to see, as I showed before, at this moment we have 2s and 3s states are combined. We would like to do the separation between these states. And this is the main goal of this detector. And this will start next year, construction. The STAR is mostly focused on the beam energy scan and is going to run all the time in until 2020, where they have upgraded all different subsystems to enhance and to look for the critical endpoint. This is the main point for this upgrade. The conclusion. The RHIC is a remarkable QCD machine as well the RHIC and provide a lot of beam collisions. We have gold, that's all this energy. We have a D gold, we have uranium. As well, this year, we are interested in the small system, P gold and P aluminum has been just done. At this moment, from the RHIC beam energy scan, the window of the search has been narrowed between 20 to 40 GeV. And we hope that by 2019, when we go to the phase 2, we can find this critical point. Something very important. The recent result from the RHIC RHIC and the proton, deuteron, and helium gold collision provide brand new insight of our field. This has been proven to be interesting and more surprising than has been anticipated before. And there is a lot of work to be understood. Quarkonia is an excellent probe to learn about the thermal and the medium of the QGP. Also, we are preparing for the future accelerator upgrade, PHENIX upgrade, as well STAR, and as well as I promise you that we have to watch for more new results in the next conference, Nucleus 2017. Thank you very much for your attention. I think it's not on. No. Oh, yeah, you have to push.
Now a few minutes for questions. I said also, thank you for a nice talk before.
You're welcome.
Can I ask a question from here?
Yes, go ahead, please.
Okay, so first of all, thanks for the nice talk, and it's quite interesting. So I have two small questions. One is about this identified particle V2 measured at BNN scan, because you indicate that the broken of the number of quarks scanning might show the critical points. But then my question is, we also observed the number of quarks scanning broken at RHIC, and how do you explain that? This is one of the questions. And the second one is, you also show this flow in PLED and
Yes.
D-gold. And
Yes.
You probably also know that at LHC, for Atlas, CMS, and Alice, we all present these multi-particle correlations. And I'm wondering whether at RHIC you have any related results for 4 and 6 particle correlation.
Yes,
Thanks.
we have also a trick. There's the particle correlation in the D-gold as well. We are working in the helium, but I'm trying to, because this is not conference for heavy ion, I'm trying to make things as simple as I can that can communicate with outside the field.
Sure.
And yes, it has been shown at RHIC user meeting last week. And I think you can just go to the web page and look there. There is a correlation, and there is they talk about the reach. And I think there is very new result, but as you say, I mean, we need to work to understand the result. About the flow, you are referring to this one here?
Yeah, sure.
Yeah. I mean, the scaling, it's working for the baryons and the meson as function of energy. And you are saying that when you go to the LHC energy, this is scaling fail. Yes, I mean, to be honest, this scaling V and divided by the number of constant quarks, I don't believe it anymore. Personal opinion, okay. We have to look to jet quenching, correlation, and other things that we can refer to. I think this one, maybe the most interesting here, which I'm showing, is what's going on with the PHIs.
Yes, because we observed number of quark scanning also broken for 5 meson. That's
Yes,
Maybe you clarify
yes. I think for the
privately.
PHI, it will be used as some kind of probe. Yes.
Just short question, with the beam energy scan in run 14, you want to go below 6 GeV center of mass energy. And can you be sure that the statistic is really good enough at 3 and 4 GeV?
Yes, let me show you something very interesting has been developed by STAR. STAR has now fixed targets inside the beam line. Yeah, they install it and they're taking the data right now since 2000, I think 14, 15, and they show some results at the RHIC user meeting. They have fixed targets inside the beam line. When there is one beam is circulating, they bring it down and they hit the target and they are collecting the data. Mostly the beam energy scan is driven by STAR collaboration. They will have enough statistics. It's like you are doing FAIR inside the RHIC.
Well, maybe this. The question was, is there a good physics reason why this should be between 20 and 40 GeV, which is conceptually convincing, not that it comes out of some computer?
I mean, you are thinking that the critical point may be below 20 GeV.
Yeah, I would say
Yes,
so.
yes. There is, at this moment, the community at LHC and Brookhaven, they work together. To be honest, they are not. There is really competing. Some people think it's below 20 GeV. Some people, based on this, they say, oh, between 20 GeV to 40 GeV. And this moment, they are really, we have to narrow the window more, with more observer to say, oh, maybe between, behind. I cannot, to be honest, I can say between 10 to 40, and let them play with it to see what's going on in 2019.
Okay, thank you very much again.
Thanks.